This is section 9.2, which is about generating functions. This is the definitions, examples, and calculational techniques. So you really should have watched section 9.1 video first, where we spent quite a bit of time talking about how to set up a generating function, which is an important skill to have, and it's going to be much easier for you to do section 9.2 if you already know how to do section 9.1. So essentially what we are doing is creating a power series, and hopefully we know enough about a power series to know that quite often we're able to take a power series and rewrite it as a much simpler expression. So this particular generating function is for an infinite sequence, and an infinite sequence meaning that I've got x to the 0 power here, x to the first, x to the second, etc. I also have a coefficient in front of each of these, and a sub 2, remember that's just a numbering system, so it's just the coefficient for whatever x squared is. So essentially what I'm looking for, if I were looking for this guy, and that's what we talked about in our last video, is what's the solution that we're looking for. So if I'm looking for x to the 30th of gx, essentially I'm looking for the coefficient of x to the 30th, that I really don't want to have to multiply or FOIL or any of those things. So we will, a little bit later on, look at how to find that value. But before that, and that's going to help us get there, is we're going to look at some generating function identities. And again, I will not be requiring you to memorize these, but it will require a little bit of organization on your part. So my suggestion to you is to make a page and keep track of all of the generating function identities so that they're easy to reference, because you will be referencing them quite a bit. Now, before we look at the identities, let's look at a brute force example. I'm starting you out with a very simple example. And in this example, I'm saying a girl can choose 2 items from a basket, and in that basket there's an apple, an orange, a pear, a banana, and a papaya. How many ways can this be done? Now, this is a simple example where I don't need a generating function to solve. In fact, I can do it just like this in this case. So, solved simply, I'm saying I've got 5 items to choose from. I'm choosing 2 of them. So, 5 choose 2. And we all know 5 choose 2 means 5 factorial over 3 factorial, 2 factorial, which in fact is 10. Great, no problem. Now what I want to do is look at how am I going to solve this with a generating function. Now, if I were actually given this question, would I use a generating function? No, I would do this because it's so darn easy. But instead, I want to show you, because this is a fairly straightforward, simple example. If I had a generating function and I was doing this the brute force way, which means I don't know any of the identities yet, essentially I would start by distributing, and I would keep doing that for x0, and I would do that for x1, etc. And I would continue and continue and continue. Now, I'm not going to bore you with all of that math, because if you're in combinatorics, you know how to multiply things. This is what I come up with when I multiply everything out. And again, you can use Pascal's triangle to help you with that, or brute force. So here's my solution. Now remember, I'm looking for 2 items, which means I was looking for the coefficient for x squared for my generating function. If you'll notice, here is my x squared value. What is the coefficient of the x squared value? It is 10, which is the same solution that I got previously. So essentially that is what this is all about, is being able to find this 10 without having to do all of the math of foiling it out to get this full solution, because I don't care about any of these other values. I only care about the 10 in front of my x squared. Now, in order to accomplish everything that we want to accomplish, we need to know some rules or identities. Now, keep in mind that my goal is to be able to find coefficients that are in front of certain values. That's our end goal. So let's take a look at what we call the fundamental identity, and that is created by taking 1 divided by 1 minus x. Now, I've shown you the long division here. And again, long division is something you learned way back in college algebra and probably haven't used a ton because, let's face it, it's not the most fun thing to do. But I'm basically taking my 1 here and dividing it by 1 minus x. And I'm not going to go through a ton of the math there because, again, the focus is not on can you long divide. But what I looked at was how many times would 1 go into 1 time. I multiplied 1 by both of those values, then I subtracted them. My 1's went away. This was minus a negative, so it gave me plus. Then I looked at how many times would 1 go into x. It would go in x times, and I continued this pattern. And we could see that this would just continue to create, if I felt like continuing on forever and ever, it would just keep going. Now, again, the importance here is what are the coefficients? Well, the coefficient is 1 in front of each of these. That is why it's called the fundamental identity, because it generates a sequence of coefficients of 1, 1, 1, 1, 1, or it doesn't matter what value you're looking at, the coefficient is 1. That's why it's called the fundamental identity. At this point, I could just give you a bunch of the rules for using the fundamental identity, but it's just so much more helpful for us to look at this in terms of how we started with the fundamental identity, and then turning it into how would I use it for a series like this. And this series doesn't have all 1's. It has all 1's, except I'm starting with 0, 0, 0. So here is the function that I want to model. So my question is, how am I going to model that? Well, essentially what I'm doing is I've got x to the third, x to the fourth, x to the fifth, etc. And I don't have an identity to use for that. What I do have, though, is I have this guy, which is the fundamental identity, which, if you'll recall, was 1 over 1 minus x. And if I take an x to the third out of that, out of what I had originally, then I've got x cubed times that fundamental identity. So what am I going to do? I'm going to write it as x cubed divided by 1 minus x. So you can see how I might represent something that has mostly 1's, but maybe starts with something other than 1. And in this case, I had 1, 2, 3 zeros, and if you'll note, I've got x cubed. So let's look at another application, again, using the fundamental identity. Now, what's different about this series? It's not all 1's, but in fact, it's a 1 then a negative 1. So essentially, we're just alternating signs each time. So again, my focus is how am I going to manipulate that fundamental identity so that it will result in coefficients of 1, negative 1, 1, negative 1, etc. So essentially what I'm looking at is the summation from 0 to infinity of negative 1 to the n, x to the n. Hopefully that makes sense to you, because this would be negative 1 to the 0, which would be 1, and then x to the 0, which would be 1, and that's where I come up with 1. And then moving on to n equals 1, that would be negative 1 to the first, which is negative 1, times x to the first. So we can see that this pattern would in fact give us 1, negative 1, 1, negative 1, etc. So simplifying that just a bit more, I've just multiplied these two terms, so negative x to the n, because essentially I just need that negative taken to the n power. And so what does that mean? It means it's the same as I was looking at before, but I've got a minus negative x, so essentially I have a plus x. Because if you'll recall, the fundamental identity was the summation as n goes from 0 to infinity of x to the n. And so essentially I'm just making it negative x to the n, and that would change it to 1 over 1 plus x instead. Here's another fundamental identity question for you to work on your own. So again, I've thrown a little bit of a curveball in here. Not just ones, I've got 1, 0, 1, 0, 1, 0, 1, 0, etc. So think about how we could use the fundamental identity, which is 1 over 1 minus x, and how might we manipulate that so that I get a 0 whenever n is odd. Do your best. This is probably not going to come naturally to you right away. You'll just get better and better at it, as anything that you do when you practice. When you are ready, press play to see how you did. So again, what I'm looking for is I want the generating function to be 1, and then x squared, and then x to the 4th, etc., which means I've got the summation from 0 to infinity of x to the 2n, because I only have even powers. So if I only have even powers, if I want to rewrite it so that it looks more like that summation as I go from 0 to infinity of x to the n, which was my fundamental identity, if you'll notice, I've just rewritten it as x squared. So what does that tell me I can do? I can take 1 divided by 1 minus, and instead of x, I have x squared, which, there we go. So that is what I've got here. That is my generating function for, that's my identity for 1, 0, 1, 0, 1, 0. Now, before looking at any of the other identities or anything like that, I want to look at this last one a bit more closely, because I want to look at my solution of using partial fractions, since that's how essentially we're going to be able to find our solutions once we actually solve one of these guys. So hopefully you remember partial fractions from calculus or Calc 2 or any of the other classes you might have learned partial fractions in. Remember, this was the identity that I came up with, and we really kind of wrote it both ways previously. Now, all I'm doing so far is I'm factoring my denominator to be 1 minus x, 1 plus x. And remember, partial fractions essentially says, let's find the coefficient for, or let's find the numerator, essentially, for each of these factors. And I want that to equal 1 over 1 minus x squared. So I'm solving for a and solving for b. And so again, I've got, if I want to write it so that I don't have a fraction any longer, I'm taking both of these times 1 minus x squared, 1 minus x squared, I guess not both, all of these times 1 minus x squared. So this goes away and just gives me the 1. This, the 1 plus x cancels and gives me the 1 minus x. This one, the 1 minus x cancels and gives me the 1 plus x. And then I'm just distributing a, distributing b, and eventually I end up here. So again, I'm looking at 0x plus 1, so I need a minus b to be 0, and I need a plus b to be 1. So the question is, where did I randomly come up with 0x plus 1? Well, I need my coefficient to be 1. I don't need there to be an x. So I've got 0x plus 1. Here's my system of equations. We can solve the system by substitution or elimination. If you'll notice, I've used elimination. I've come up with a to the 1/2, or a is 1/2 and b is 1/2. So rewriting it, replacing a with 1/2 and b with 1/2, I end up here. And then essentially I'm looking at replacing this guy with my original fundamental identity, and replacing this guy with that other application of the fundamental identity, where I had the 1 plus x instead, keeping those 1/2s out front, if you'll notice, 1/2 and 1/2, and that simplifies to this. So the big question is, well, what was that for? Why did I have to do all of that? Well, keep in mind, my goal at the end of this is going to be to find something like, find a 30. something like that. And so if I'm able to rewrite in a situation like this, I don't have to FOIL anything out. I can just use that summarized formula to then find the coefficient for 8 to the 30th, or 8 to the 100th, or 8 to the 1000th, etc. Here's another one to try, and this one is decidedly more difficult than the last. Notice I have given you a hint to try differentiating each side of the fundamental identity. So I'm going to leave you with that hint, but remember our goal here is to come up with basically the series of natural numbers, 0, 1, 2, 3, etc. So give it your best shot. If you're not up for the challenge, feel free to just go through it with me. This one is a little more difficult, obviously dealing with calculus and differentiating each side. When you're ready, press play to see how you did. So remember, the fundamental identity essentially says this, that if I'm taking the summation from n goes from 0 to infinity of x to the n power, then it's equal to 1 over 1 minus x, which gives us the function 1 plus x squared plus x cubed, etc. Now, if I take the derivative of everything, well, the derivative of this would be n times x to the n minus 1. That's how we do derivatives. The derivative of this guy would be essentially using that quotient rule. Bottom times the derivative of the top minus top times derivative of the bottom over the bottom squared. We end up back at 1 over 1 minus x quantity squared. And then if I take the derivative of 1, I get 0. The derivative of x, I get 1. Derivative of x squared, I get 2x, etc., etc. So essentially I have come up with the pattern that I want. And remember, the pattern then, in this case, because we want to start, we want this guy to be x. Notice it's missing an x. This guy to be x squared, etc. I'm going to multiply everything times x. So multiplying everything times x, I would get 0, I would get 1x, I would get 2x squared, I would get 3x cubed, etc. So again, notice that if I'm multiplying by x, it changes this to just to the nth power, because I've added a power essentially by taking it times x. And I end up with the expression that I wanted, 0, 1, 2, 3, etc. So again, that's another identity that you'll want to keep in mind using where we started at the fundamental identity, but it is essentially a new expression that you might use if you're looking for the series 0, 1, 2, 3, etc. And just one more using the fundamental identity, and then I promise we'll move on to, say, a geometric progression or something a little bit different than just the fundamental identity. So again, using any of the strategies that we've looked at so far, see if you can come up with how we might represent the series 0, 2, 4, 8, 16, etc. So again, look for the pattern here. It's not just even numbers. Look for how we might use the fundamental identity to come up with that series. So again, I'm looking for a sub n x to the n. I'm replacing it with 2x because essentially if I replace it with 2x, that would be 2x and then 2x quantity squared, which would be 4x squared, and then 2x quantity cubed, which would be 8x cubed. So you get the idea. All I'm really doing is taking that fundamental identity and replacing this guy with 2x, which means, just like we did with some of the other ones, I'm just replacing that 1 minus x with 1 minus, in this case, 2x, and that is my identity that I would use for 0, 2, 4, 8, 16, etc.